let's talk about STPA scenarios. So for a while, we've had a number of people ask for more formality in the scenario generation process. And we've had a new process in development for the last 10 years and really wanted to test it to make sure it was working well before we rolled it out to everybody. And now it's time. It's working. It works really well. And I want to share how the new process works and the results we've gotten. So first, let's talk about the goals, why we wanted to develop a new scenario process. There is already STPA step 4 to develop your scenarios, and the handbook provides a little bit of guidance about that, but we wanted to do something a little better. I'm going to show you the process. Most of the time will be spent on how the actual process works. And then we'll talk about some of the results we've gotten in the last 10 years from the guinea pig companies who have been rolling this out and comparing it to other approaches. So this has to do with STPA step 4, identifying the loss scenarios. So I'm not going to talk about the other 3 steps. If you're not familiar with STPA, you should look at the handbook or the other tutorial videos to understand step 1, losses and hazards, identifying the system boundaries. Step 2, modeling the control structure and identifying the control loops in your system. What are the controllers? Could be human controllers, could be automated software controllers or some other type of controller. What are the control loops? What are the control actions? What are the feedback paths? Step 3, where you analyze the unsafe control actions. These are always going to be downward arrows in your control structure. These are the means you have to affect change in your system and achieve your goals. But the control actions could be unsafe. And so we want to identify how they can be unsafe in step 3. And then we get to the last step, step 4, which is identify the loss scenarios. So why would a controller, whether it's human or software or something else, why would a controller issue those unsafe control actions? Why would it think that's a good idea? Some of the reasons could involve failures. Some of the reasons may not involve any failure at all, as we'll see in examples today. And we want to identify scenarios where the controller did the right thing, but we still had a hazard and a loss despite all of the controllers sort of doing what they were supposed to do. And so there's a lot of scenarios to cover in step 4. And that's what we're going to talk about today. We're going to skip over the first 3 steps and jump right into step 4. So one of the comments we've gotten from folks is they love the first 3 steps in STPA, especially step 3, where you have a lot of rigor. You have this very careful syntax that you follow to help you make sure you're writing something that's really a valid UCA, an unsafe control action. It might look like this. A computer provides a shift to park command when the vehicle is moving. This might be from automotive, some piece of automation to help you shift. And you definitely don't want to do this while you're moving because you're going to strip out the park pawl in your transmission and you won't have park when you need it in the future. And so there's a very careful way to write this in STPA step 3, a special syntax to follow. And you develop these really formal UCAs. In fact, they're so formal that you can translate these automatically into a set of requirements. And the requirements are written in such a strict way that they're executable. You can generate automatically state machines and state charts and execute transitions in your concept before you've actually done any design, just using the UCAs from the careful structuring that's done. And so a lot of folks have said, well, that's great, but it's in stark contrast to STPA step 4, which involves a lot of sort of open brainstorming and thinking. Can you make STPA step 4 look a bit more like this? So that's what we've tried to do. The goals were to provide more scenario guidance because new practitioners sometimes get stuck and they appreciate a little bit more guidance. Provide a formal structure for scenarios, something similar to the UCA syntax that most folks love. Provide a way to review these scenarios. So someone dumps on your lap at 20 pages of scenarios. How do you know what's missing or where the gaps are without sort of just relying on your gut instinct? We develop a formal process to identify those gaps? And hopefully we can handle more complexity by using a top-down approach, a true top-down approach, and not just a backwards search approach in scenarios. Now, before I go any further, I want you to know that the scenario approach in the handbook is still pretty good. People have been using it for 10 years and presenting at the MIT Stamp Workshop the success that they've found using that method. And there are advantages to the existing method in the handbook. So I don't think that's going away. And I think we want to be flexible. So if folks want a more lightweight process that doesn't have strict rules and guidance, you can still do something very quickly using the process in the handbook. And I think that's still legitimate. But there are other folks who want something very structured, very careful, with, in fact, more guidance. It may take a little bit longer to perform as long as it has more guidance and more structure. So that's what I'm going to show you. Let's do a quick review of hazard analysis search strategies. So you can understand the ingredients to the new scenario approach and sort of know if you're doing things right or not. This comes from Nancy Levison, in fact, who surveyed the field and showed you can look at different types of search strategies in a hazard analysis method, like an FMEA or a fault tree or event tree analysis or anything else. There are some common search strategies. There's a forward search strategy, similar to an event tree analysis, where you have to start with some initiating event and you're basically going forward in time. And that's your sort of guiding principle as you develop a scenario. You start with some initiating event. Usually it's a failure event, so you're a little constrained with the types of things you start from. And then you go forwards in time. How does that propagate to other systems or other impacts until you get to a hazard? You can do the same thing in reverse with a backward search. Some folks view FMEA as a backward search, starting maybe with a failure mode or maybe a failure effect. In aviation, there are 5 effects that are defined for the industry, and sort of working backwards. What are the causes and the mechanisms that lead to those failure modes and effects? That would be a backward search. So your guiding principle as you develop a scenario is just go backward in time, right? So the time is sort of the variable that we move forward or backward through in this scheme. But there are other approaches. There are bottom-up approaches where you start with a set of individual component failures, and then you look at combinations of those and how they propagate to a higher level hazard. This is not necessarily going forward and backward in time, because the statement at the bottom could be the exact same moment in time as the statement at the top. The difference is in abstraction. You may start with a very detailed low level of abstraction at the bottom, and then sort of bubble that up into more abstract statements. Not necessarily going forwards in time, although you may, but the guiding principle is abstraction, going up in abstraction from those bottom level events or failures. And then there's top-down search, which has a lot of advantage for dealing with complex systems. This is the winner, no matter which approach you're using. This strategy has so many advantages when it's a very complex system with many interactions, possibility for unexpected behaviors and other things. This starts at the top at what you might call a hazard, a sort of very short and very abstract definition of what we want to prevent in our system. Like 2 aircraft get too close to each other and they're in danger of colliding with each other. That would be a top level event. And it could be the exact same moment in time as some lower level failure. It could be before, could be after in time, but it could also be at the exact same moment in time. Time is not the guiding principle here. The guiding principle is starting with that high level abstract definition and going down into lower levels of detail and maybe enumerating all the individual component failures that would coincide with that top level event. Or maybe we don't want to be limited to failures. We want to look at more detailed sort of states that might be involved in the high level sort of super state, if you will. So the top down approach is what we want to use in any scenario building a process. Let's do a quick review of the old process that's described in the STPA handbook. We exit step 3 with a set of unsafe control actions, and we begin step 4 by identifying scenarios that have something to do with those UCAs. So we can go backwards, starting from the UCA. This is a control loop, which you'd be familiar with from STPA step 2 and 3. And we take the UCA and we basically go backward. We sort of go upstream and say, okay, what controller, decision-making characteristics could lead them to select that unsafe control action, make them think that's a good idea? What beliefs in the process model could make the controller think that's a good idea right now? What feedback could sort of trickle through the controller and their decision-making and cause them to issue this UCA? Could the feedback be delayed? Could be missing? And a bunch of other things. And this, again, this is still very useful. I don't think it's reasonable to throw this away totally and say no one's ever allowed to do this again. This is very valuable. It's also very, very quick. And folks have been very successful using this approach. It also requires a lot less training to understand and to learn. You basically just have to understand how the control loop works and the types of things involved in feedback, process models, and decision making that lead to these decisions. Once you understand the model on the screen, it's fairly easy to just go back and say, okay, I've got a set of beliefs. What kind of feedback is going to inform that belief? And that's sort of what the handbook does. You also go in the other direction. This would be sort of going forward from the control action, going downstream and saying, okay, say we issue this control action. How can it maybe not be executed by the rest of the system, maybe by the hardware or other things? Not executed properly, like we command a door to open, but it doesn't open. We command thrusters to turn on, but they don't actually turn on. And it could be caused by failures, of course, so it includes those things, but it may be caused by a non-failure, which is what most people found very useful about this. Look at this guy. Controller issues conflicting control actions. That could happen maybe without a failure. Maybe both controllers are doing what they were intended and designed to do, but nobody foresaw they could conflict in this way. And so the control action may not be executed properly. That would be an interesting non-failure case. And so we still want to pick up all of these cases in any new approach. But the steps to get there may be a little different. One of the challenges is if you've got really complex control loops or complex controller software making these decisions, it can be a time consuming, and the tree can sort of branch quite a bit. And if you imagine starting from a UCA, let's go to this slide. Imagine starting from a UCA working backward. You can have almost endless branches if it's immensely complex and have a large number of things to consider all at once. And there isn't really a shortcut to going step by step, decision making, external control inputs, process model, feedback, sensors, sort of going step by step like that. There isn't a really strong shortcut when you're just going one step at a time backwards. Anyway, so there are advantages and disadvantages to this approach. The backdrop for this talk is going to be the Mars Polar Lander example, right? So if you haven't seen this already, I'm going to take a couple minutes and walk through one of the problems that occurred. And we're going to use this as we go through the scenario approach to sort of reason about how you would apply this, how you would think about different classes of scenarios and how you would write them out. So this was sent to Mars a while back, and during descent, it's got to slow itself down. You don't want to crash into the surface. So it deploys a parachute, as you can see, releases the heat shield, and then it lowers these landing legs. You can see in the picture. Let me change my cursor. Here are the landing legs that deploy at a certain point during the descent. And then it turns on these descent thrusters. And when the computer comes down to the surface and touches down onto the surface, there are sensors in each foot pad. So there are 3 of these feet, 3 of these touchdown sensors. And the computer will look and make sure there's agreement in these 3 touchdown sensors that we have indeed touched the surface. These are basically vibration sensors, if we simplify it a little bit. And as long as all 3 agree that we have touched down at the same moment in time, the software has got a really important job to cut power to the descent thrusters, and it will command them to turn off. And that's obviously important. You don't want this thing to bounce up or flip over. We'll lose the mission on Mars. So here's what actually happened. During the descent, the legs deployed as planned. And the way this works is they drop down onto these mechanical stoppers, all three of them. And of course, all three drop at the exact same moment during the descent phase right here. And that happened exactly as planned. They dropped down and they hit those mechanical stoppers. But guess what? When they hit the mechanical stoppers, it caused a vibration in the foot pad. And this happened at the exact same moment for all three legs and all three foot pad sensors. They detected a vibration. The way the sensors are designed, this is an oversimplification, but it works. If the vibration is over some threshold, it reports a true signal out of the sensor to the computer. And so all three sensors reported true at the exact same moment in time to the computer. It's not technically a failure because they did exactly what they were designed to do. The intended function was to flag true when the vibration is over some spec. So the spec was met perfectly by all three sensors. They sent out a true signal to the computer. And what did the computer do? Well, it did also what it was designed and intended to do. If all of the foot pad sensors agree, and it was called a touchdown signal in the design, if all three touchdown signals equal true, the software is designed and required in the requirements to issue the cutoff signal, the command to the descent engines to shut down. And the computer did exactly what it was designed to do. And guess what? The whole thing was destroyed. It free fell, hit the surface at 50 miles per hour. The engineers at the time had said there's no way it's going to hit more than 5 miles per hour. That's what we're going to design the whole thing for. It crashed and was totally destroyed. 110 million US dollars gone. And what's fascinating about this to think about is what failed. Well, you might argue the mission failed. We didn't accomplish the mission, but what actually failed in the Mars Polar Lander? The components all did their job, all achieved their individual component functions at the lower level. And somehow the whole program was lost. The whole mission was lost. And so there's an interesting discrepancy here when you think about failures in a hierarchy. There's something that doesn't quite connect. And that's something we want to catch in STPA. So this is going to be the backdrop as we go through generating scenarios in STPA. So I know it's a little bit of cheating, but this is going to get us through real quickly to learn the approach. And then later you can apply this to other systems where you have a little bit more time than we have today. Okay, so let's look at a control loop, and let's do this the old way first, and you'll see how it works, and it does work. What's the UCA? So we have a disable thruster command. That's a control action from a thruster controller. This would be some computer on the Mars Polar Lander, and it decided to do something with this command, right? So open up the chat for me and let me know your ideas of what the UCA might be. Yeah, there's several different ways to phrase this. You guys have got the issue, right? It should not be shutting off the thrusters when we're in flight, when we're still descending, when we're not on the ground, right? Any of those is legitimate. That's the issue here. So let's write that down as a UCA. Computer provides disable command when it's still in the air. And that's a disaster. We're going to crash, right? But why would a controller do this? And one way to do this, let's skip to process model beliefs. What did the controller believe at the time that made it say, hey, let's disable the thrusters now, right? So we're enumerating a process model that can cause this. We're just going around the control loop. This is the old way of doing scenarios. Yeah, the computer believes it was on the ground. It believed it did touch down onto the surface, right? So we write that down as a process model, and that'll cause the UCA. Now, where does the process model come from? It's actually not random. A lot of folks argue that these kind of unsafe behaviors, maybe they're random because they only happen, X% of the time. But actually, this is not random. We try hard to make sure software doesn't virtually flip a coin to form a belief or issue a control action. There is a reason for the decision, even when the decision is wrong. So what's the reason for the process model? Feedback in this case, right? Feedback, it has to do with this arrow here. We're sensing something from the lander using a set of sensors, right? So you can imagine, if you will, buried inside this arrow are a set of sensors called touchdown sensors. And they tell us a piece of information called touchdown. Touchdown signal, touchdown feedback is the information that's provided to the controller. And what was the state of that feedback? What was it telling the controller? Just to play out the rest of this scenario. It basically said touchdown is true. It received a touchdown indication, and it was 3 out of 3, in fact, right? Because they were trying to guard against failures. If any one of the sensors had failed, it would have been protected. One of the reasons this was not protected is it was something more complex than what you typically think of with random failures. And we can go one more step, right? We started here. We're just going in a circle. What was the controller thinking? What was the input to the controller? And now let's end with, what was the state of the lander? What was truly, truly going on with the lander? Well, it was truly in the air. We actually know that from the UCA. I'm making these connections, even though we're talking about the old process, I'm making these connections that we're going to keep in the new process. This is called the context of the UCA, this part, this when part, when it's in the air. And that's telling us the true state of the process down here. So we know it really was in the air, but it's sending the wrong feedback because there was vibration. So if you ever have that combination, if you ever have vibration in the air, it's basically putting together this bubble and this bubble. That's all we're doing. We're saying we're in the air. That's the state we're in. And we're saying somehow we've got this touchdown indication, which is a vibration indication, right? They just called it touchdown, but it's really a vibration sensor. So if we've got this vibration that looks like touchdown and we're in the air, right? That's how you get this guy. If we've got vibration in the air, we're in trouble. We're hosed. We've got no strategy to deal with this. The design is flawed. The requirements are flawed. Even without a physical failure, even without a component functional failure, we can have this dangerous interaction. So it does work. The old method does work. Now let's do this using the new approach. Okay, so how are we going to do this? This is going to be a formal process. And at the end, we're going to reflect on the pros and cons of this approach. It does have some disadvantages, but it has many advantages as well. It is formal. It's going to take a little bit longer for us to go through. It's a little bit more education is needed to understand the rules, because there are more rules now with the formal process. We'll review all of those at the end. Here's what it looks like. Okay, so we're in STPA step 4. We're going to start in the problem space. Always start in the problem space. What can go wrong? What is my loss scenario that's going to get me to a hazard? Right? So this is where the process of discovery happens, where you say, aha, this can interact in this way. I never realized it before. So we're going to start by identifying these high level scenarios. It's not going to be, 5 sentences, 20 sentences long. It's in fact going to be 2 sentences every single time. That's a high level scenario, exactly 2 sentences. And I'll tell you exactly how those sentences are going to be written. But you can't say that much in 2 sentences. It's going to be very broad, very abstract definition of a scenario in the first part. Then we're going to immediately go to the solution space and say, before we get any further and spend a lot of effort, let's see if there's something we want to do immediately to sort of strike against this very broad, high-level scenario and maybe eliminate it completely. Maybe this feedback really doesn't belong. It's just going to confuse the controller. There's something better we want to use instead, for example, or totally change the concept. Maybe we want to do that before we've spent a lot of time on the wrong concept. And then once we've thought about and identified potential high-level scenarios, maybe there's some scenarios we can address easily. Maybe there's some we can't. We want to look in more detail and identify refined scenarios. So in some way, we're going to add detail to those high-level scenarios to see what the detailed causes, the detailed factors that are going to be involved. And that's going to help us come up with maybe better solutions, maybe identify solutions we haven't been able to think of yet, and build a better system. So we're going to do this in sort of two phases: high level and a refined, more detailed level. So here's a little bit more information. These high level scenarios are going to be broad and abstract, like I said, and they're going to have a formal syntax. There are, in fact, going to be 4 classes of scenarios that we're going to define, and that's going to guide us throughout all of these steps. We're going to show how to review, how to show coverage over those 4 classes, show some measure of completeness, or at least comprehensiveness over those 4 types of known classes that need to be analyzed and addressed. We're going to identify some high-level solutions, and for each class, we're going to see some patterns. Different types of solutions are going to match different classes of scenarios, and we can use that to be a little more efficient when we try to engineer a system. And then we're going to refine each of those scenarios, and you're going to see the 4 classes have different types of refinements that we're going to do, and then we're going to identify solutions for those. Okay, so what's going to guide us throughout all of these is the definition of 4 classes of scenarios, 4 types of scenarios that we need to show we've done our homework and examined. Let me pause for a moment. I'm going to glance at the chat. I don't think I've seen any questions or anybody stumbling yet. Is everyone with me? Is this making sense so far? But you're anxious to see the details, is what I would assume. Or is anyone totally confused? If you are, let me know. Perfect. Okay, so here are the 4 classes. Okay, now at the end of this seminar, I'm going to connect these to what's in the handbook. So this is actually right in line with what's in the handbook. It's just more guidance and a little bit of a different way to get there. But it does line up with the things in the handbook for STPA Step 4. And I'll pull up the handbook figure at the end of this, and we'll compare it to these 4 classes. Class 1 is the case where you have an unsafe control action. So the controller did something unsafe, but some feedback, some input or feedback was good. And we'll define what that means in a moment. It gets a little tricky to define this, but I'll show you what that looks like. Just don't dig into the details yet. Just soak in the 4 classes. Some information was good to the controller, but the controller still made a bad decision. And this class 1 is going to take us into the controller decision making. We're going to ask the question, why would you do that, even though you had some good information in some way? Why did you do that? And this is going to draw us into the controller to explain how this can happen. Class 2 says the controller did something unsafe, but it was lied to, right? So the controller sort of did something unsafe, but it was given unsafe information, right? So it sort of didn't have much hope of doing something better, since it was misled or given unsafe information. And this is going to drive us at a minimum to explore why the feedback was unsafe. And we may do more than that. We may also look at the inside the controller and other things. But at a minimum, why was the feedback messed up? In class 1, we're not so interested in why the feedback was unsafe, because we had at least some good feedback. There is, class 1 can involve some feedback things, and class 2 can involve some controller things. We'll flesh that out later. But this is the essence of the classes. Class 3 says actually the controller did the right thing. It didn't commit any unsafe control action, but something happened down here so that it's as if we had a UCA. It's just as bad. Either, a simple case would be some kind of corruption along the control path, but another more interesting case would be maybe there was another controller that got in, and this could be safety or security. It could be another controller that, conflicted with what this controller was trying to do. So, this controller didn't provide a UCA. There's some interaction downstream that we care about. That's class 3. And then class 4 says, maybe there's nothing at all wrong with the control path. The control was applied to the process, and it was the right thing to do, but the process ignored us for whatever reason. The process could be software, could be hardware, it could even be other humans. But for whatever reason, the process did not do what the control action was trying to command. And that's certainly possible. And that's class 4. Okay. Yeah, actually, all of these often boil down to something wrong with the design. Again, all of these could involve failures if you think about it, right? Class 1 could involve, controller failed. Could be, solder, tin whiskers in, some CPU or whatever. It could be one of the scenarios, but there could also be a non-failure for all of these classes. And we will look at that in just a couple minutes. Okay, let's do class 1. I think class 1 is the most interesting out of these 4. So we're going to spend the most time on class 1. It has a lot to do with decision making, with a logical sort of processing of information through the controller. Okay, so if we want to sort of map this onto a controller, this is what it might look like. We've got a UCA, right, that came out of the controller, and we've got to look at least a couple different cases, right? So one way to zoom in on a focus area is to look at the feedback, condition on the feedback. And this is what I was saying about instead of going one step back at a time, which is a backward search, and it involves a lot of tree branches along the way. What if we, just sort of skip to the end? Let's do what's known as a transfer function. Let's look at the output of the controller, so UCA, and let's look at the input of the controller, which is usually feedback, although it could be other inputs. That's why there's a slash here. Usually it's feedback, but it could be other inputs. Feedback or input was adequate, right? So it was okay. It was safe in some sense. We'll define what that means in a moment. It needs to be real crisp, which we'll do. But it was okay. The controller sort of was told that this is what's going on and it was correct, but the controller still did this unsafe thing anyway. And there are some reasons that might happen. We got to look at that. That's class 1. Later in a moment, we're going to look at class 2. Class 2 says, yeah, the controller did that, but the controller was given bad information as well. Okay, so let's look at class 1. So we're structuring, and see, we're going to have this fill in the blanks as we start. And by the end, we're going to have a real crisp syntax to follow for all of these. But to start with, how do we structure this? So some input is correctly showing some piece of information to the controller, right? And what information is relevant here? Because there may be 100 inputs, right, to a controller. Are we going to condition on all of those inputs? No, we're going to do the one that matters. And how do we figure that out? Well, we actually had the answer in the UCA. It's the context. The context is what's most critical for preventing this UCA. The context is the state of the system or the outside world that makes the control action unsafe. And so one of the critical things is the controller needs to be aware of that context, right? Basic control theory. That needs to be indicated on the feedback somewhere for the controller to make a better decision. And so class 1 says, we had feedback that correctly indicated the context. Now, we're not saying anything about the other 99 inputs if they exist, right? We'll flesh that detail out in a moment. All we're saying is there did exist one input that correctly indicated this context, and we got to explain why the controller sort of did the wrong thing anyway. And there are reasons why this has happened, and it's caused accidents. So this is how you write a class 1 scenario. This is a high-level scenario. We say the output is, and it's just the UCA, just write the UCA. Controller provided the control action when context. And the input correctly showed where the context is. So we have to identify the input, we have to identify the context. And that's our class 1 scenario. Now, there may be 100 reasons, 100 different reasons why this could happen. That's fine. That's why this is top down. We're not going to enumerate all of the reasons. We're not going to, branch the tree a million times going back 1 second in time each step. We're going to try to capture a large swath of scenarios with a simple high-level statement, because maybe we can do something in the design to totally eliminate this. One example, maybe we remove this control action from this controller's responsibility. Maybe it's a software controller. We say, well, actually, we don't want this to be automated anymore. We want to do something else. That might be one way to address this scenario, this whole class of scenario. Let's figure that stuff out before we enumerate all the 100 different causes. So this is a high-level scenario. And this is all of these archetypes are going to use the concept of a transfer function. If you're not familiar, it's basically the idea of we have some box that is doing something. It receives inputs and it provides outputs. And without knowing how the box works or what's inside, can we describe the unsafe behavior in terms of input and output? Can we describe what unsafe controller behavior means by saying if you get this input and you provide this output, that is unsafe. You should never do this output when this is happening. Of course, it naturally leads you to some questions. Why? Right? As soon as you've got this high level scenario, you're going to immediately start thinking, why would a controller do that? And that's crucial, whether it's a human controller or a piece of software automation or something else. And so we have to refine the scenarios at some point. And you can refine it by asking a simple question, and then I'll show you a more elaborate way to refine it. A simple question that you can use all over the place is, tell me the failure reasons for this decision. Now, although it fits into STPA, there are a lot of different methods to get the failure causes. Fault trees, FMEAs, there are all kinds. So most people, although it is included in STPA, most people feel like that's not the novel piece of information you get. What's really novel are the non-failure explanations. How can the controller mess up and make an unsafe decision even though it worked perfectly with no failure? And it gets real interesting. Can the controller have another priority, right? Could it have a default behavior? Could it default to something if something else is going on or something else is received? Can the controller receive some other piece of info? Because notice in this transfer function definition we're using, we're just saying that one input correctly showed the context. There may be other inputs that conflicted, right? And so that needs to be included somewhere. Maybe the reason the controller ignored this input is because it got another input somewhere else. And it said that one's more important or that one's more trustworthy, which is an assumption, right? That could be made during engineering. Maybe the controller provides the UCA because there's no other control action that's better, right? So in a car, you may be talking about braking, steering, and acceleration. And you might say, why didn't you brake? Well, maybe the reason the controller did not brake, the UCA for an object, did not brake for an object, is because there was no other better decision to make. Steering maybe was ruled out for some reason. And we would examine that. So this is, I'm just showing you some examples. We're going to make it formal in a moment. But you can identify this high-level scenario. This is a decision-making scenario. You got input that correctly showed the context, and you made the wrong decision. You provided a UCA. Why would this happen? And there are some interesting reasons in addition to the failure cases, right? So let's map, as we go, let's map all of these onto a generic control loop. This is class 1 scenario archetype, and it describes inadequate controller behavior or unsafe controller behavior. The UCA comes out even though the controller had some good information. It wasn't totally missing. It wasn't totally wrong. It had some good information, and it made an unsafe decision as a result. That's a class 1 scenario. Let's try it for the Mars Polar Lander. Okay. So let's fill in the blanks. The controller, this is the thruster controller we're talking about, provides what? Well, we already did this, right? Provides the disable thruster command when spacecraft is in the air, right? That was the output. How can we write this? What was the input? The input was touchdown, right? Touchdown signal or touchdown indication to the controller. Correctly indicated, that's not what happened, right? So this is not going to match what actually happened in the Mars Polar Lander, but it's going to be another scenario. Let's do it anyway. Let's see what this would look like. Input to the controller correctly indicated what? Out of the 100 inputs that may exist, what input is relevant here? Do you remember? And do you remember where it comes from? It comes from the context right here. right? I like this. This is traceability to sort of make this more formal and to minimize, this sort of ad hoc brainstorming we rely on. Let's add traceability everywhere we can. And so we're going to use this context to identify the inputs that matter. I love that. And we're going to do this for every single scenario we develop. We're going to have full traceability, and that enables you to review and to identify gaps. If someone submits to you an STPA set of scenarios, you're going to be able to review, following a set of rules, what was missed or what was covered. Yeah, so let's imagine it correctly indicated the spacecraft was in the air. That's not what actually happened when it actually crashed into Mars, but it's a scenario. It's a legitimate scenario, actually. It needs to be considered. So how can the touchdown inputs correctly indicate it's in the air, but the computer still provides a disable thruster command when it's in the air? That's fascinating, right? Isn't it interesting to think about? And it turns out there are some other inputs that potentially could confuse the computer. There was actually a radar altimeter that the computer was looking at in addition to the footpad sensors. And there may be some way the altimeter feeds bad information, even though the footpad sensors work. The altimeter may feed some information that causes the computer to override and disable the thrusters anyway. And there may be a bunch of other cases to think through. But that's interesting, right? Anyway, do you see the pattern? We are refining these scenarios, right? So on the left, we have the archetypes, which are the high level scenario statements, and it's always going to be 2 sentences. And those sentences are going to be very structured and follow a syntax, just like UCAs are. The refined scenarios are going to look at a set of factors that explain why a controller would do this, right? So I'm going to show this on the left and on the right. On the left will be the high level scenarios. On the right will be the refined scenarios. Why would a controller do that? Well, it's designed to default to some state. Aha! If the computer boots during descent, which is a part of the design on the Mars Polar Lander, if it boots up during descent, does it have a default state or default output that is provided until it finishes its calculations? That could be an interesting scenario, right? May not require a failure. Could the controller have also received some other input? So it appeared reasonable to disable the thrusters. Maybe something with the radar altimeter, right? And so on. Now, this part on the right so far feels a little bit ad hoc, right? We're going to make it more formal in a moment, but I think there's value to ad hoc as well. We could stop right now and you could go use this and do really good. Develop some really powerful scenarios. We know because we've tested this with real companies and real engineering projects, and this alone has been extremely useful and outperforms what was previously in the handbook and outperforms any other method, fault tree analysis, FMEAs, and others. Now, we'll talk more about that at the end. But you may want to be even more formal. You may want to totally eliminate this ad hoc part of scenario development. And to do that, we need a model, right? So we can use a generic controller model to help you ask better questions and find actionable causes if you're looking for more guidance and more step-by-step process to develop scenarios. Here it is. So back to the transfer function, right? This is the class 1 archetype. We've got the UCA coming out, and we know that there was at least one input that correctly indicated what was going on. And our question is, how can that happen? What can be going on inside the controller that could cause it to issue this UCA? Well, here's a generic controller model. We've got some decision-making process. If it's software, sometimes it's called a control algorithm. If it's a human, we would just say decision-making. Some decision-making process that we're using to select this control action, right? This could be informed by a set of responsibilities or procedures, informed by some idea of what the current state of the system is. And if we mess up the decision-making basis, if we have gaps in responsibilities or we have conflicting responsibilities, or if we have a poor understanding of the current state, that's going to mess up our decision-making, right? So those need to be included in our causal factors when we refine basic scenario class 1. We also have the process model. What are our beliefs about the states? And there's a little bit more to process models. You can expand this. What is the belief about the current state? What is our belief about the future state or the capability of this thing? What is our belief about the dynamics of the process? Meaning, if I hit this button, what's going to happen? That's another process model. It's a dynamic process model, but it is a process model. And we can identify those beliefs that can cause the controller to issue the UCA. We also have interpretation, which is how the process model gets updated over time. And interpretation may be based on some feedback. It may be based on some assumptions about the system. So, 5 seconds have expired since I did this, then I assume something else is going on, for example. So we can identify how does that controller update the process model based on feedback, usually, but it could be other information or control actions from up above. Your supervisor came down and commanded, or a human operator overrode the software mode and commanded through this control action from above, you shall do this, or you shall, apply these limits to the feedback or whatever, and affect how the controller makes decisions. So we can actually enumerate these and build them formally into the refined scenario. How would a controller make this decision? Well, we've got at least 6 categories of reasons why this class 1 scenario architect would happen. And if you're evaluating a set of scenarios for completeness, you can go through each part of this model to make sure that it was evaluated and considered. Look at the responsibilities that would produce this UCA. Does the controller have some other responsibility aside from slowing descent, for example? Is there some other? A great example from another project is we were looking for responsibilities using this process, and the software engineer said, yeah, there's a responsibility to do that. My responsibility over anything else in the software is to prevent invalid state transitions. And we were sort of shocked to hear that, because that was not really the responsibility of the controller. But it was sort of inferred and assumed by the engineers that that trumps everything else. If it's an invalid state transition, I don't care if it's going to cause mayhem. I'm going to just stop the entire machine. And that's interesting. Probably a different decision should have been made. The responsibility probably was to ensure safe states. If it's invalid or not, let's not just shut everything down. Let's make sure it goes to a safe state. So how can it, anyway, that was a tangent. Apologize for that. But how can the responsibility of that controller, one of their responsibilities, cause the UCA, even though they have at least one piece of good information from feedback? How can control algorithms of decision making maybe prioritize the incorrect things and cause the UCA? How can the process model belief, and it's not just beliefs tied to that feedback, it could be beliefs about something else, beliefs about whether we're in an emergency situation, and maybe that trumps everything else in the controller. Interpretation, internal controller states or modes, like a lame duck mode in automotive. If something goes wrong, it'll default to the lame duck mode, so that it provides degraded functionality. And that may have a side effect of causing some UCAs, or causing it to ignore feedback that might actually be working, right? Controller inputs, that would explain this, conflicting, contradictory inputs, all that stuff we had before, it's still in here. We still want to consider it, but we'll do it in a refined scenario now, instead of going backwards one step in time and branching the tree every time we go back another step in time. Okay, so we can go through a few of these, and all of this comes from real projects, but I've had to scrub the details so we can talk about it. So I've sort of put them in blanks for each category. So responsibilities, maybe by design, the controller is responsible for assigning whatever the control action is, even if something else is going on, right? So this has to do with, maybe the wrong priority. And there are different types of responsibilities we want to look at. There are fixed, hard-coded responsibilities that cannot be changed. An example of that was in the autonomous aircraft AI presentation by the U.S. Air Force a couple of weeks ago in the virtual stamp workshop. The limits of the software were hard-coded, and that ended up being a problem because the test team did not want to test at the airframe limits design limits that would rip the wings off the aircraft. They didn't want to test anywhere near those limits. And they wanted to really make the limits more conservative for testing, but they weren't able to. So that was an interesting example of that. Dynamic responsibilities that may change depending on what's being sensed. Um, uh, um, they're being provided in real time. And adaptive, right? So the difference between dynamic and adaptive is whether it's in response to a control action or in response to feedback. And so these categories can help you identify these types of responsibilities. And you can see what I'm leading up to at the end of this presentation is when you compare the resulting scenarios, you get incredible richness of cases and richness of solutions that sometimes are more effective and cheaper than what you might have considered using some other approach. Control algorithms may fall back onto some other strategy, right? Maybe that's the reason why it ignored the feedback and provided the control action anyway. Of course, we have process models. That is always a cornerstone of STPA. We also have to look at interpretation of inputs. In some situations, the controller might interpret this input as something else, right? And these are all real things that have been found. So maybe even though the feedback technically correctly indicated something, maybe it was interpreted incorrectly inside the controller as indicating something else. Maybe there are conflicts between the feedback. So this just says we had a feedback that correctly indicated. There may be conflicts. There may be other pieces of feedback, previous feedback, minutes, hours, days ago. We're also including human controllers. Past experience plays into this, right? That may cause them to doubt whether this correct feedback is actually any good. And we could develop a table like this to look at how the process model may be updated. And there are a number of categories to consider if you want to get into the details of this and be real careful about it. How can the process model not be updated? This may occur because the feedback was not provided to trigger an update of the process model. Maybe the process model was stuck in some default initial value, some belief. This happens all the time with software. When it first boots up, the variables have to be initialized to something before the first feedback is received. That could be the reason. Feedback may be updated incorrectly. It may be updated too late, and the same exact thing for feedback. Feedback could be provided incorrectly, could be updated too late or too early. Process model could stop updating too soon, and so on. Do you see a pattern? This is the same categories we had from UCAs, but they also apply to process models and to feedback. And you can get that in the class 1 scenario architect because that it explains why a controller would do this thing anyway. Okay, so we're just taking the same categories and just using them on the feedback path to be super rigorous about this and to provide more guidance to folks who may feel like they are still learning and worried about missing something. Let's look at states and modes. This was labeled by E in the model. So all of this is grounded in a controller model, generic controller model, and you may adapt this to your own applications. But this is pretty good. If the controller is in some mode, maybe it'll continue doing the control action anyway. And that will lead to the UCA. Even if the feedback changes, it may be stuck in some mode that sort of ignores the feedback. Maybe the controller is disabled effectively and is no longer listening to feedback. So the fact that the feedback was correct doesn't matter anymore, right? Because it was in this special mode that's effectively ignoring the input. All of these could be designed and intended features, but of course, no one intended it to cause a UCA. But we have to think through carefully, right? Not just how the failures can lead to UCAs, but how the behavior of the design or the concept could lead to UCAs, especially as things get more and more complex. We might look at alternate inputs. So maybe the controller does not prevent a control action. We'll look a little bit later at the different permutations. This says provides. That's because of the UCA2 that we started with. We'll look in a moment at the different ways you can look at UCAs. although the input may be correct, there may be some other feedback that's incorrect and causes the controller to do something else. Okay, so that's class one. I find class one to be the most interesting. So we spent a lot of time on class one. The other classes we're going to spend a little bit less time on. And I think it's going to start to click for you because we're going to apply the same pattern, the same sort of transfer function style to all these other classes. We're just going to look in a different part of the control loop. Let's look at class two. So class two says, okay, there was not a good feedback telling you about the context, right? Either it was totally missing or it was lying to you or it was delayed or one of those other cases. There was not a good feedback. So this is sort of everything but class one, right? You see how that works out? Class two is sort of the everything else that was not included in class one. So, all right, so put a big check on class one. The feedback was okay, and we issued the UCA. Now we're looking at a different class. We're looking at how the feedback sort of contributed, how the feedback was inadequate. It did not tell you that that was the context, or the feedback was totally missing, or it was delayed, or whatever. That's class two, right? So it's going to lead us to focus a little bit more on the feedback path. And of course, another interesting thing is you can have combinations, right? You can have these different scenario classes can combine. We'll talk a little bit about that at the end. You can think of these as sort of building blocks to building your scenarios. Okay, so let's look at class two. So we're looking at sort of this part of the control structure, and we know in class two, there was something wrong with the feedback for sure. Feedback did not adequately indicate something, fill in the blank. Well, what, out of all the 100 pieces of feedback, what's actually important for UCA2? Well, it's in the context here. Whatever the context is, that's the crucial state that makes the UCA unsafe. That's the crucial feedback we're going to look at. And if we have UCA3 with a different context, and we're going to look at a different type of feedback. But we're not going to sort of take a list of all possible feedback and just say, what if that one doesn't work? What if that one doesn't work? We're not going to do that because it may or may not matter. We're going to start with a UCA because if the context doesn't appear in a UCA, we're not going to analyze it because it doesn't matter for our purposes. All right, so let's look at class two. That's a way to be efficient when you've got many, many different types of feedback. You don't want to just brute force it. You want to be smart about the types of feedback you analyze and prioritize them as well. Okay, so class two, we have some bad feedback, unsafe feedback at the top being fed to the controller. And some UCA context is true, right? So we know there's some state of the process that doesn't match the feedback being fed to the controller in some way. That's the class two scenario architect. That's the 2 bullet points. This is basically just taking that transfer function concept and applying it to feedback, right? So how can feedback to the controller not indicate this context, right? Which the controller needs to know to prevent the UCA, but the context is true, right? So we put those side by side. Context is really happening, but the feedback sort of lies in some way. That's our scenario 2 archetype. There may be 100 reasons why. But we start here and we look immediately for solutions. What can you do about this? Well, you may, at the concept stage, identify a totally different type of feedback to complement this one. You may decide to change the controller's responsibilities. Maybe make it no longer responsible for responding to this context or this feedback. Maybe change it so that another controller with better information or better reasoning skills, like maybe a human, is able to do something different. So there are solutions you can identify right off the bat at this high level, potentially. And we would start there. Eventually, you may need to refine them. And so if you want to just quickly get a sense of how to think about causes, make sure at a minimum, you consider failure and non-failure causes. One of the biggest mistakes folks make, particularly on feedback, but really everywhere, is they only look at failures. This is usually folks who are very new to STPA. They're very used to something like a fault tree, which is all about failures and combinations. And they try to take that sort of mental knowledge and map it onto STPA. And so when they look at feedback, they often say, oh, the speed sensor failed, or speed sensor malfunctioned, right? Or the pitot sensor froze. They'll sort of enumerate failures, and it's sort of interesting because it is a valid STPA scenario, but you're sort of missing the point. The point is to especially capture the non-failure cases. And so at a minimum, make sure that you've considered both, not just the failure causes. And so you can take sort of you can just take what's on the screen and sort of get with your design team, go to a whiteboard and say, what are the reasons that this can happen? How can this UCA context be true, but the feedback doesn't indicate it? And it could be because some metric is being estimated and it uses a different basis. Could be because the feedback actually is outdated. Even though it does get through, it's delayed and outdated because there's a 10-second feedback delay because of the way the sensor or whatever works, right? Another non-failure case that can be interested. These why answers in gray, right? So this is refining the basic scenario, may come from the SMEs, not always the STPA practitioner. So don't feel like the STPA person has to have all the answers. You really complex projects, there's no one person that knows everything. So typically, we'll talk about this at the end of the seminar. Typically, you would have someone who knows the process that I'm showing you, the STPA practitioners, and then their job is not to come up with all the answers, but to come up with the questions, right? To present to an SME, hey, how can this be happening, but the feedback says X? And we've tested exactly that. We've tested taking these generated high-level scenarios to 1, 2, 3 SMEs at real companies on real projects to see, can they, number one, can they give us an answer, or are they totally confused because they don't know STPA? If they understand the question, are the answers they give useful? And every time we've done this, the SMEs come back with mind-blowing answers that no one had ever considered before on the project. So that's fantastic. It exceeded all of our expectations. Just coming up with this question, how can this process be in this state, but the feedback says this? Or the feedback is delayed. And I'll show you those categories in a moment. I actually already showed you previously those categories. It's the same categories from the UCA. All right, so let's formally define class 2. Formally, class 2 says something about the input and the output of the feedback path. So how can the process actually be in some state down here, but the feedback spits out something else? Either something else in a different point in time, or some other type of indication or granularity or whatever. All right, so let's try it for the Mars Polar Lander, right? Let's fill in the blanks here. What is the feedback or input that's crucial from, let's go to the next slide. So let's take our previous results. We've got UCA 2, we've got the class 1 definition. Here's class 2. What's the feedback input that matters for our analysis here? Yeah, the feedback we're talking about is the touchdown indication, right? Which comes from the foot pad sensors. There may be 100 other inputs, but that's not what we're focusing on right now. Let's look at how the touchdown indication to the thruster controller did not adequately indicate what? Well, the context is right here. Did not adequately indicate that it's in the air. And the process, which is the Mars Polar Lander, is actually, context again, is actually in the air. Okay, you see that? Do you see how this comes out and how it's very rigorous about how these are written and where the information comes from, right? All of this information actually came from the work we've done. We're just putting it together to define a feedback related problem. Touchdown feedback does not indicate that it's in the air, and the lander actually truly is in the air. How can this possibly happen? And remember, at a minimum, you've got to think through the failure cases and the non-failure cases. Failure cases are easy, right? Sensors fail. You probably would have to say all three sensors need to fail because it's using three redundant sensors. So that's your scenario. All three sensors fail. Okay, what else? How about a non-failure? How about all three sensors work? All three sensors work and they indicated touchdown in the air. Isn't that interesting, right? And so you take that basic scenario, this class 2 basic scenario, and you bring it to an SME and you say, I'm working on this problem. How can we possibly have a touchdown indication in the air, but the sensors are working? Touchdown indication, we're actually in the air, but the sensors are working. Given those three pieces of information, this is actually what Google presented at the virtual stamp workshop. Give the experts those three pieces of information, and they'll give you brand new flaws in your design that no one has identified before. But if you would like more guidance than just saying consider failures and non-failures, we can do that. Let's define what we mean. What does no failure mean? It means whatever's on the feedback path, typically it would be sensors, but it could be anything. It could be a telephone. If you're talking about humans receiving feedback, maybe in a control room from somewhere else or air traffic control or whatever, it could be a telephone, right? It doesn't have to be, an angle of attack sensor. How could the sensor actually work as specified? Well, what does work as specified mean? What does it mean? Well, if we wanted to ask an engineer, what does working mean? What does the non-failure mean? You go to the specification or the requirement, right? For the sensor. What does the requirement say? Requirement says when vibration is over X, spit out touchdown equals true. That's actually a transfer function, right? That's the required specified behavior of the touchdown sensor. And all we're saying is that's what happened. The sensor operated true to its specified behavior. So stay with me here. I hope I don't lose anybody. What does it mean from this class 2 scenario? We know it really is in the air. We know the touchdown feedback says true. The sensor reports right here, touchdown equals true. And we know the sensor works. This is the rule for working. If output equals not in air, then input equals vibration greater than X, right? That's the transfer function for the sensor working. If we're talking about case 2, no failures, these have to match, right? That's the definition of a non-failure. These have to match. The input and output of the sensor have to match. So if the output is touchdown equals true, the input must be vibration greater than X. Do you see how we got that? We got it right from the specified behavior of the sensor, right from the requirement. So this scenario is telling us, how can you get touchdown feedback in the air? And we must have vibration over X. How can we get vibration over X in the air? That's what it's telling us, right? It's just algebra, right? It's just basic algebra, essentially, for case 2, no failures. It spits the answer right out. Somehow you get vibration in the air. That's the case, right? It comes right out of this process. Okay, so you can do this, just sort of take this basic 2 bullet point scenario to an expert, say we need some failures and we need some non-failures that explain this. You can get really good answers. And in practice, we found that works surprisingly well. I was sort of doubtful because it's not super rigorous, but it blew my mind every time we tested it. That actually worked really well. But if you want to be even more rigorous, you can use a basic model of the feedback path to identify the kinds of problems that matter. How can the feedback be missing? How can the feedback be not provided? Missing is different than not provided. Missing means it's not even on your block diagram or your concept to begin with. We never thought of including the sensor for this piece of feedback. So missing is a different case than not provided. Not provided means the feedback path exists, it's right there, but it's not sending anything right now. Consider both cases: conflicting feedback, incorrect feedback, too early, too late, measurement inaccuracies, dropouts, corruption, content incomplete, feedback provided in a way the controller can't use. That's super interesting when you've got complex software interactions, information being broadcast over a bus. This absolutely has happened. Technically, the feedback was there, but the controller couldn't read it, couldn't figure it out because it was, any number of reasons. Overloaded or too much feedback. That's an interesting case, right? Too much feedback. We think about excessive UCAs already, it's defined in step 3. The same thing is valid for feedback as well. And you can use that to refine the class 2 scenario. Okay, so some examples: feedback can be sent too early before something has occurred. You never say too early, period. This is also true for UCAs. You're not allowed to just say, feedback is too early or control action is too early, period. You have to define, what do you think too early means, right? And so you would always qualify this by using the word before. If it's too late, then you use the word after. And that's already built into the UCA syntax. It's right there in the handbook. But you can do this for scenarios as well. And that's what we're doing here. Feedback is not provided when, right? You recognize the formulation there? It's just like a UCA. Feedback is not provided when blank. We've got to figure it out. When does it matter? We actually have it. It's in the context here. If the process becomes overloaded, there may not be any indication of what's going on. So this would be feedback, again, would be missing. These scenarios are used to help us think about mitigations. I'm not going to spend a whole lot of time in this seminar talking about mitigations because it depends on your application. STPA is not usually going to tell you this is the correct design. It's going to tell you here's what's wrong, and it's going to tell you you need to think of a mitigation for it. And once you have a mitigation, it'll roll that into the analysis and say, here are the weak points and the vulnerabilities of that mitigation, right? So if you add feedback, you'd put that into the control structure. If you add a control action, you'd put that in the control structure. You'd identify UCAs for the new mitigation and so on. But it's not going to tell you this is the one correct design, right? That's an engineering decision process. So these scenarios are helping you think through what the vulnerabilities and the flaws are and help you think about mitigations, but it's still your job to do that. It's going to tell you currently your design has no way to protect against overloading, and you've got to figure that out. All right, class 3. Class 3 looks at the control path. We've already exhaustively looked at UCAs in class 1 and 2. We've looked at UCAs when at least one feedback is okay for the context. We've looked at UCAs where there isn't a good feedback for that context. That covers everything because they're inverse of each other. So what's left? What if there's no UCA, technically? What if the controller does the right thing? It spits out a good control action, a safe control action, but it doesn't work. And there's a couple of reasons it doesn't work. One is the control process gets an unsafe control action somehow. How can that happen? Well, we're now going to study the control part of the control loop, and we're going to look at how the UCA could be emulated due to some interactions in the system, and they're highlighted on the screen. So a simple example would be maybe the actuator fails. That's real simple. Anybody can come up with that one, and you don't need STPA to think of that one. STPA is just one of the many ways to do it. But what if the actuator doesn't fail? What if it operates as designed, but the design has a half-second delay because the actuator has a response time? Another interesting one is the controller sends a conflicting control action, right? So there may be a lot of different reasons. How do we do this top down, right? How do we avoid just going one delta forward, one delta forward, one delta forward, and we branch a tree at every delta because that explodes? how can we manage the complexity a little bit smarter? Well, use the transfer function concept. We define a class 3 scenario archetype, and we say the controller does not provide some control action, but the process receives it anyway. Now, if you're going to start using this, pay attention carefully to the way this is written. This starts with a UCA. This is a type 2 UCA. It's a providing control action that's unsafe. And if we want to emulate that UCA, what we do is we say the controller didn't do the UCA, right? So the controller does the opposite. The controller actually did not provide a UCA. The controller actually didn't do it. But it's as if the UCA happened, because something in the downstream path, something in the control has sort of caused the same hazard we were concerned with in the UCA. So the process still receives. Now, it could be, something just goes wrong in the actuator, something goes wrong in the path, could be corruption. Those are trivial examples. But we want to look at non-trivial examples like, notice these other arrows, maybe the same control action can come from multiple sources. Maybe another controller can provide the control action. So the process still receives it, but my controller didn't do it. And that is a design problem. We've got to think through how are these controllers going to coordinate with each other? How is the control process going to prioritize different commands that it receives and so on? Also, clearly, it could be a security issue, right? So these same classes of scenarios and the same process applies to security as well as safety. And that's been demonstrated in the trials that I'll talk about in a few minutes. So we now have our class 3. Let's try this for the Mars Polar Lander. Now, this is not going to be exactly what happened on the Mars Polar Lander. We already covered what really happened. We captured it right here. But let's postulate it to see what it looks like. What would a class 3 scenario look like? So the controller is the thruster controller, right? Does not provide. What's the control action? It's the disable thruster command, right? Notice it's different. It's different than what actually went wrong. And the actual problem, the actual crash, it provided a disable thruster command. We're postulating a different scenario, which is a legitimate one. Does not provide disable thruster command when what? How are we going to fill in this context? It's the same. When it's in the air. Right? So the controller did the right thing, actually. The controller did not provide disable thruster command when we're in the air. That's a safe thing. That's not a UCA. That's a safe thing. So controller did a good job. But it didn't work. The process somehow receives a control action. Which one? The disable thruster command. Receives the disable thruster command when spacecraft is in the air. That's our scenario. Our controller didn't do it, but somehow this guy receives control action in context. Now, in the security world, this could be a number of different things, spoofing. Look at if there's wireless communication or an override that can be sent. But in the safety world, this has happened, not on the Mars Polar Lander, but elsewhere in the safety world. We've done this to ourselves. For example, by uploading brand new set of coefficients to a satellite that messed up the inertial reference system and caused the satellite to spin out of control and totally destroyed the satellite. That has happened. And that would be a great example of sort of the ground station, another controller, sending an overriding control action that sort of overrides what our own onboard computer is telling it to do. Right? So that would be a class 3 scenario. It could also be maybe there's some delay in the control path. Maybe, this is interesting, if you read the details of the Mars Polar Lander, it's actually fascinating. Anyone who's familiar with how software works or a software engineer, you should go read the report from JPL because it had this latching behavior. The thruster controller actually would provide the disable command at something like 1,000 feet of altitude, but it wouldn't get executed. It would just latch and stay in memory that the thruster controller attempted to shut down the engines at 1,000 feet of altitude. It would not execute immediately because it had some other software interlocks. But it would remember the request indefinitely. And if you came down to 40 meters, 120 feet, and this had previously sent the request at 1,000 feet, down at 40 meters, the thruster controller is actually doing the right thing, is actually no longer saying shut off descent thrusters because it's no longer getting vibration signal. So the thruster controller now is actually doing the okay thing. We're at 40 meters and everything's good. But because it previous command had latched down here in the control path, as soon as that software interlock was removed, which was from the radio altimeter, as soon as it gets below 40 meters, that software interlock is removed, and the previous command from long ago now gets through and executes, right? And so this is a legitimate case to think through, right? It gets more interesting than just simple failures. Okay, so we can refine class 3 as well. What can cause this scenario archetype? And in practice, actually, there's a little more guidance coming up, but in practice, we found just taking these 2 bullet points to your SMEs is really fruitful. It'll surprise you how fruitful it is, especially if you tell them specifically, I already got a bunch of failures. I'm looking for the non-failures. How can it technically work as designed? But this happens. We get a command. Even though the controller is not providing it right now, we still get a command out the other end to execute. Could it be buffered somewhere in the control path? Could it be, saved and then unlocked by a software interlock? And that's surprisingly fruitful. So already, if you just understand how to write these bullet points, you can get pretty far, actually, with this process. And here are some examples. Some other controller could send the control action. You could send the control action with an ignore bit. This is a fascinating example we got from an automotive autonomy stack. It had a capability to do the right thing, but set the ignore bit, which effectively is not providing a braking command. If you say brake with X deceleration, but ignore the command. That's an interesting thing to think through, right? And it was missed by the original folks who didn't use STPA. And when we applied this process, we caught it. So that brings us to class 4. Hopefully, you're starting to get a little more comfortable with this transfer function concept. You can almost maybe imagine what this is going to look like. It's going to have something to do with inputs to the control process and outputs of the control process, right? Let's take a look. We need to look at how the UCA could be emulated. In other words, how we can cause the exact same hazard, but instead of being caused by the controller, how can it be caused by the process itself, right? So we already looked previously at conflicting control actions, delays through the actuation, and so on. So let's look at what's left. What's left is this is good. This is right. We got through, we told the process, now you shall brake. And maybe even we started applying brakes, but it didn't work. The process output was incorrect. We did not decelerate the car, even though we applied the command brake. The car did not decelerate. How can this happen? Well, process input could be missing or wrong. What's that mean? What's a process input for a braking system? It gets into the details, but we could say something like maybe in a physical hydraulic system, if we're looking at brakes, maybe the hydraulic fluid is missing, right? We're missing pressure because we've got a leak, right? That would be a physical failure, which is included in this process. All right, so the way you construct class 4 at a high level scenario, these 2 bullet points say something about the process input and something about the control action applied, right? So let's do it for the Mars Polar Lander. So process does not receive what control action? Does not receive a disable thruster command, right? When it's in the air. Good, that's perfect. That's what we want to see. No disable thruster command in the air. But wait, the process, which is the vehicle itself and the thrusters, apply the disable thruster command when it's in the air. So essentially it cuts out thrusters when it's in the air. It's the same hazard, same effect as the UCA, but it was not a thruster controller doing anything wrong. It was something down here. How can that possibly happen? Immediately, you'll think of failure cases. The thruster could fail, could run out of propellant, a whole bunch of stuff. Could there be any non-failure cases? More interesting than that. Potentially. Any ideas? Let me know in the chat. So we're trying to explain this class 4 scenario. How could that possibly happen? Oh, I love it. Could the thrust be diffused by some obstruction? So interesting, right? Not the first thing you think of. The first thing you think of is always a failure, usually, if you're used to doing failure methods. But these are just as legitimate. We got to think these through. Okay. So we are refining class 4 right now. What can cause this? And just presenting this to an SME, someone who really knows the mechanics, is surprisingly fruitful. But if you want more guidance, you can identify a list of things that have been known to come up before. There may be some mechanical property of the process. There may be some limited physical supply, whether it's fuel or hydraulic pressure or whatever. There may be some capacity involving that process that automatically triggers some other behavior. The process may have mode. The process may be physical and mechanical, which is where the first bullet point comes from. It could also be a software process, right? We could have a hierarchy of software controlling and supervising other software. So the process could be in some other mode. And in some mode, it may ignore all of the inputs and commands. It may default to some other behavior. And so we can use this to come up with more refined scenarios. All right. Now I'm ready to show you this table. Look at this monstrosity. My gut reaction is immediately I don't like it. But if we go back to our goals in the beginning, people want more structure, want more guidance, want much more formal syntax, just like the UCAs. It does have some advantages of providing a review basis to know if you missed some scenarios that are important. And for people new to the process, how do you know you're doing it right? And it is much more careful than the ad hoc approach we do today. This is basically what we just did summarized on a table. Here's how this works. We have, from the previous step, 4 types of UCAs, right? So we could have UCA 1 that we start with and build scenarios against it. We could have UCA 2 providing something, and we could build scenarios against UCA 2 and so on, right? So depending on your UCA, you're going to identify which column you're looking at right now, right? Let's look at this one. Not providing causes hazard. The Mars Polar Lander example, we just went through this column. The UCA was providing the disable thruster command when you're in the air. So that's a type 2 UCA. And so we went through this column. So if the UCA is you provide some command, we want to look at class 1, right over here, class 1. How can we provide that command? And we received feedback that told us we were touched down. Or sorry, told us we were in the air. That's the context. Told us we were in the air. How could feedback tell us we're in the air and we still disabled thrusters? That was class 1 scenario. Class 2 scenario was the feedback did not tell us we're in the air and we're actually still in the air. How can that happen? And so on. If it's a not provided UCA, it's slightly different. The UCA starts with not providing the command. And the feedback looks like this. You received feedback that indicated the context. Right? The only difference is the command is the opposite. It's not providing. Over here, feedback did not adequately indicate context. Context is true. That's the same. Controller does provide command when context because it's the opposite of the UCA, right? The UCA is the controller does not do. That's unsafe. We want to consider in class 3, what if the controller does something safe, but it doesn't matter? It sort of doesn't matter because the process misbehaves anyway. So we invert the UCA, right? The UCA is not providing, we invert that. Does provide, controller does provide command. It's not the UCA, it's a safe command, but it doesn't work. It's not effective, or it's not followed. Command is not received by the process, and so on. Type 3 has to do with timing. And so it's very similar, but the timing issue sort of propagates. We want to think about timing on the feedback path, timing on the control path. Sorry, I skipped class 1. Class 1 would be timing of the decision making, right? So if your UCA says you provided too late, one of the reasons could involve the decision making was too late. Another reason could be the feedback was too late to make a decision on it, right? In fact, you could have both of those. Feedback could be delayed and the controller process decision making could be delayed, right? And we do the same thing for the downstream piece, right? I don't expect this to make 100% sense. Really, what you need to do is to start practicing this. And as you practice, especially if you have an instructor over your shoulder to correct your mistakes, you can start to get really comfortable following this process, just like folks have gotten with UCAs in STPA Step 3. If you look at the little tags in here, like the controller is a tag, it's like a fill in the blank. Command is a tag, context is a tag. If you look at the tags, the information, actually, most of it comes from the UCA. Most of your work is actually buried in the UCA, which is nice. It provides traceability so that you have a basis to review the scenarios and to know what's missing or what else needs to be considered. Anyone have any questions at this point? Again, it's your first time seeing it. It's a lot to take in, but does it basically, did it flow? Do you sort of see how we went through these 4 classes because we started with a type 2 UCA? Do you see how you'd have to do some sort of inversion, even though you don't have all this memorized? Does it make sense to you that we'd have to do some sort of a slight inversion to look at scenarios where you don't provide a UCA, right? Great question in the chat. How do you feel about using this more formal process as a QA, quality assurance function, for the old process? That's actually what we did. I think I've got 2 slides and I'll show you the development of this historically and what's given so much confidence that we're really ready to make this the formal process for folks to follow. In every comparison that we did, using this as a QA comparing to the old process, this captured everything we have ever found in STPA. And it found a handful of new cases that were missed by the original teams. And my name is on some of that original work. And applying this process to look back and realize what I forgot was pretty powerful. Okay, so let's tie this back to the handbook. This is totally in line with what's in the handbook. It's just a lot more guidance and a lot more formalization. But these figures appear in the handbook from 2018, the STPA handbook. And the text that goes along with these starts with the UCA and sort of works backward 1 step at a time. This is backward search. And then it gets into feedback and it goes through here. And then it starts with the control action. It goes through the control path and goes through here. But look at the numbering. This is class 1. And the name of class 1 is unsafe controller behavior. This is class 2 that we defined today. And the reason for that is we had this process when the handbook was written. I personally didn't have a huge amount of confidence. I felt pretty good about it, but we know folks are going to be using STPA as safety critical things. And I wasn't that sure it was always 100% of the time going to give you a better result. I really wanted a lot more testing to be done. So intentionally, I wrote the handbook to be consistent with this method if this is the path we went. So this method doesn't violate anything in the handbook, and it complies with all the criteria in the handbook. So we would have the option, if it worked out, to sort of release this and show folks additional guidance behind this, but it doesn't violate a thing. That's where these numbers came from, in fact. And so this method has been tested for over 10 years. We just kept it low key until now, because when we release something, a lot of folks start using it immediately, and it always sort of gets you concerned. A lot of folks think we just come up with an idea and then write a paper and tell everyone to start using it without vetting the idea. That's actually not what we usually do. Before STPA was recommended to anyone in industry, there was maybe 15 years of folks using it prior to the handbook in 2018. Of people using it in the industry to give confidence that it really does work. It really is not going to embarrass us to put our names on this. And I sort of had the same feeling about the scenario approach. Really wanted to be absolutely sure that this always works and always gives a better result. And so over 10 years, what are there? 15 tests. These are just the ones that were published in a report. There are many, many others that never got written up in a report. All of these compared side by side the old approach with the new approach. And about half of these also compared it to existing hazard analysis methods like fault trees, FMEAs, HAZOP, and others. And so at a minimum, all these compare old and new STPA scenario approaches. And about half of these compare on top of that with existing hazard analysis methods that are used, that are very popular in industry, like fault trees. And every single evaluation that's been done found that this new process you just learned outperformed everything else. There has not yet been a case where the new process missed something that was found by any other means, whether it's old STPA or some other hazard analysis method. I'm sure it's going to happen one day. I don't think anything is actually perfect, but so far we've not encountered that case where it missed something. And in every case, this new process found more interesting gotchas that were missed originally. So that's very encouraging. And that's the reason that we're ready to release this and tell people this is now the formal way to develop scenarios. If you want to use the old way, that's fine. It's more ad hoc. It's quicker is one of the advantages, but it's not as formal. It's not as rigorous. I regret this covered up my text. Let me fix that real quick. The last evaluation was actually done by Google, and that was a really complex set of systems that we applied it to. We applied it to a number of different systems at Google, pure software, extremely complex. And that's what really pushed it over the edge. If it can handle this thing that nobody in the world understands, no one person in the world understands, and handle it really well and outperform, their own experts who lived and breathed it for 10 years. And we come along with this new process and find all these gotchas. That really was the final pin, if you will. It's time to release this and let other folks start using it and sort of believe in it. So here are some observations. It's not totally across the board advantageous. There are advantages and disadvantages. So disadvantages, it has more rules and structure. Some people like that, totally fine. But some people may not like more rules and structure. I mean, when you're very, very early in a program and you don't have much design information, things are much more ad hoc, maybe you'd prefer something that's less ad hoc. So go with the old process. It still works. It has worked for many years. The new process takes longer to teach and learn. And I've sort of gone through the process, but you really need to practice it. You need to make some mistakes and then have those mistakes corrected by an instructor to really learn. And so it takes a lot longer. And when I teach this in classes, it takes more than double the amount of time to teach this process than the old process. It's unclear if it always takes longer to perform. It takes longer to teach for sure. Sometimes it takes longer to perform, but it was also very new. So everyone applying this was doing it for the first time. So it's a little unfair. But in some cases, it actually took less time to perform. In fact, over the last 10 years, the cases where I tended to pull this out and try it are the cases where I was overwhelmed using the old process and felt like we took on way too much workload with this project. What are we going to do? Let's try this new process, and used it because instead of producing 100 different scenarios or 1,000 scenarios, it produces exactly 4 for every UCA. So if you've got 20 UCAs, which is typical, so produce no more than 80 scenarios, which is manageable. And it may sound like a large number, but this is massive, massive projects that we're talking about. That is a reasonable number, much better than any other approach I've seen. The same projects would have tens of thousands of failure conditions, functional failure conditions, and failure modes for an FHA or an FMEA. Tens of thousands. Anyway, so what are the advantages? It's a directed search. So we use this at software-intensive companies like autonomous software or pure software products. We use this to sort of do a better than a code review. Code review is very linear and sort of says, experts just read through the code one line at a time. It takes forever and it's extremely expensive to do, and you can still miss stuff. What we do is made it much smarter. We said, here are the 4 STPA scenarios we're looking for. What region of your million lines of code is relevant to this class 1 scenario? And usually we would find it's only this 100 lines of code. And then we would review that 100 lines of code, but not looking for anything that looks wrong, right? Which is very subjective. We would look specifically for hooks that would trigger that class 1 scenario or enable that class 1 scenario. And we did it same for class 2 and so on. So it enabled a much more directed search than what folks normally do in a design review or an early concept review. This has been applied to concept development. What makes a good ConOps? Well, the good ConOps needs to describe not only the control actions. Usually we find the control actions are the first thing you think about, but it also needs to explain the basis for the decision-making, right? Which is something to do with feedback. And it needs to explain who's going to be responsible, what groups or entities are going to be responsible for making those decisions. Is it going to be the human operators or the autonomy or something else? Even at a high level, and it needs to include those ingredients. So you can use this to make sure that your concept is defining how it's going to prevent those 4 high-level types of scenarios. It's always captured additional cases, either a handful of additional cases or many, many, many additional cases we never thought of. Particularly in class 3 and 4, we see it's underrepresented when you just do STPA sort of ad hoc. When you do it formally, class 3 and 4 always generate more interesting things. If you're ad hoc, class 3 and 4, this would be, control path doesn't work or the process doesn't respond. Most people just think about failures and then move on. But this process really helps to force you to realize there are interesting interactions in there that may not be failures that can cause the same thing as a UCA. There's less repetition. This one maybe is the biggest advantage, really. When you do scenarios normally, or the old way, there's a huge amount of repetition. So say you've got 20 UCAs, right? And each UCA has got a bunch of scenarios. All 20 UCAs may have a scenario that has the same process model, right? So the same sort of incorrect belief may appear in almost every scenario, even for totally different UCAs. And that's an example of repetition. It's valid. The process model can lead you to do a lot of different things wrong, not just one thing wrong. So it's valid and legitimate, but the repetition sort of It says something about the efficiency of the process, and there is an opportunity to do better. And that's what this process does. The class 1 scenario would only appear once. In fact, if you have 2 UCAs and they tie back to the same class 1 scenario, you could just cite the other class 1 scenario. Just do it once and cite the other class 1 scenario. And so it gives you a way to avoid repetition. And if you're in the software world, you know this very well. It's the whole reason for defining functions and modules and classes, to avoid repetition. And now we can do this in the hazard analysis. I think it makes total sense. In fact, one of the evaluations of this was on a self-driving car, the total software stack. We presented this, I think, in 2016, although we didn't say a whole lot about the method. We just presented it as one test case. And we counted the results and the size of the final report. We had a team do sort of pure STPA according to the handbook, and we had a totally different team. These were mostly software experts looking at the software autonomy stack. We actually found the funding for a totally separate team with no contact to the first team. And we matched the expertise and everything. And we had the second team use this new process in 2016. And they found many more scenarios. But at the time, we thought the most profound result was actually that the final report from team 2 was actually shorter than team 1. And that sounds like a contradiction, right? How can you have a shorter report? I think it was, we had to define a scope. And for the scope we defined, the report was 20 pages for traditional STPA, and I think it was 12 or so pages for the new process. So almost half as much stuff in the report. How could it be half as long and include more stuff? And the answer was it avoided all the repetition. The report by the new process team had all the content, but it had almost none of the repetition. And so you read it and it's very readable, and it packed a punch to read through, because every sentence was like, whoa, you gotta be kidding me. That too. When you read the 20-page report, it's like, whoa, that's interesting. Okay, I already saw that. Okay, I already saw that. Okay, I already saw that. It's the same process model as before. It's the same feedback as before, and so on. So that's actually an interesting result. Clear exit criteria. So a lot of work now on contractually requiring STPA on government programs, military and civilian applications, and in the supply chains as well. How do you contractually mandate STPA, make sure it gets done right, not just checking boxes and claiming it's done right? Well, this process provides some clear exit criteria. You can review, every single UCA needs to have all 4 scenario classes identified and refined, and you can make sure that they're done properly because of the traceability between them. This is interesting. Remember, we looked at that table and we said, we talked about that traceability. We said, look at this. We're talking about context. We're talking about control action, talking about the controller, and so on. And all that information is actually in the UCA. If you write your UCAs carefully and follow the syntax, that makes it machine readable, so that a software tool could read your UCAs and parse them. And actually, it can automatically reassemble them to create every one of these archetypes, these 4 classes. That I'm talking only about the high-level classes. You can automatically generate the 4 high-level scenario classes for every UCA with no human input, if you define your UCAs properly. Now, refining the scenarios cannot be automated. You still need a human, you still need subject matter experts. So it's not totally automated, but a part of it is. We've also compared different teams following the scenario process. And what we found is the old way of doing things was reliant on who you have on your team and having the right knowledge and experience, which really is not even unique to STPA. That doesn't matter what method you're following. You're going to rely on the expertise of your team. But it meant that one team might get a scenario because that person experienced something personally. Another team, maybe some small portion of the time, maybe would miss that because they didn't have the right experience. This process improves consistency. I don't know if I'd say that it's perfect. I don't think any method in the world is perfect, but we did see improved consistency. And I've done experiments in my classes where I would compare across 20 different classes with the same project, same problem statement, have them do STPA. And the consistency is much higher, like word for word consistency using this new process. It's almost identical result every time, which makes it easier to review and to have confidence in your results. So those are the advantages, but it may not be right for everybody because there are disadvantages. Last thing I'll say, and we'll have a few minutes for Q&A. So think of your questions. How do you run an STPA project? If anyone is new to STPA, I suspect a bunch of you are, just know you're not expected to know this inside and out, right? There are typically three types of folks who would contribute. There are the practitioners, which is who usually I'm talking to, folks who are or potentially want to be practitioners. They need to know something about STPA. So they need some basic training class and hopefully practitioner certification, but they may not be experts. They may not know everything inside or out. That's what we call a facilitator. So a facilitator would be the person that knows this slide deck inside and out. Every single word is sort of understood. The practitioners don't have that bar. They have to know what the 4 scenario classes are. They have to have seen some examples. Hopefully they've done some exercises. But it's okay if they make mistakes, because the recommended process is to apply this with a facilitator, access to a facilitator. They might not even be working full time. They might just be part-time, sort of on call or whatever the equivalent of that is. And if you've got a large organization, maybe you've got a facilitator that helps support multiple teams of practitioners doing STPA. So don't feel like you need to be a total expert in everything that I've presented to do STPA. Go try it. Lots of people have found benefit, even though they make a couple of mistakes here and there, they still outperformed everything else. And so don't be shy about trying this, and sort of relieve yourself of self-criticism that sometimes we have to try to be a perfectionist before you even try, because best practice is to have a facilitator. The burden is on the facilitator to be perfect and to know inside and out and to answer the tough questions and to catch mistakes. So as long as you are at a level of being ready to try it out and sort of understand the difference between the 4 classes and the kinds of problems, class 2 has to do has a lot of focus on feedback. Class 1 has a lot of focus on the controller. I think you're ready to go try it and to be sort of coached by a facilitator.